Okay, so we have capillary electrophoresis as a method for separating things that are charged. We have MEKC as a method in a similar format for separating things that are neutral. And we're all set, right? That's the whole story. Not so fast, I'm afraid. To get at this, I want to start just by introducing a tiny little piece of terminology we did not talk about yet, which we probably should have. And that is the type of capillary electrophoresis we've talked about is often referred to as zonal or zone electrophoresis. Zone electrophoresis just implies that small injection plug is a zone in which sample exists, and we rely on different zones to migrate at different velocities, and we get 1, 2, 3 zones would correspond to 3 peaks. So it's just a little bit of terminology, zone, as a way of talking about separations of injected plugs where the plug is considered a zone. Okay, so in zone electrophoresis, the type of electrophoresis we've already talked about, we know that the electrophoretic mobility, which governs the speed at which these things move, is going to be proportional to how charged this thing is and inversely proportional to its hydrodynamic radius, its size. And so we say that separation in zonal electrophoresis is on the basis of the charge to size ratio. So you have things of different charge to size ratio, you get different velocities, and therefore you get separation. Here's where this gets a little tricky. Here's why I say that the two techniques we've talked about are not yet the whole story. That's because in some cases, I'm going to look at two very specific cases. In some cases, Z and R are not independent variables. They rely on each other. And that means that as one changes, the other changes, and you can get in a situation where there's a very narrow range of ratios or no range at all, one value of ratio that you can get out of different sizes and charges. Let me show you a classic example, right? So the classic example of this, the most dramatic example, is DNA. Now, I'm not going to draw out DNA structures, mainly just because it'll take too long, but you may know, hopefully you do, that DNA is made up of these, it's basically a polymer of nucleobases. We give them letter abbreviations, A, T, C, and G. So let's imagine a very short DNA chain that is just an A, a T, and a C. So each of these carries with it a phosphate on the DNA backbone, and that phosphate has a single negative charge. And so that means that the Z for this thing is, well, it's -3, but we'll just give it absolute value 3. The Z of this thing is 3 at normal pH in an aqueous environment. The size of this molecule, the hydrodynamic radius, well, I can't give you an exact number on this, but I can tell you it's proportional to the fact that it has 3 bases. So it's proportional to some arbitrary value 3. So how does that compare if we had, let's say, a different molecule, ATCG, 4 nucleobases? Well, the Z is going to become 4. And that radius is going to grow, that size is going to grow, and these generally act like linear polymers, and so the size is going to grow exactly proportional to the addition of another base, and so the hydrodynamic radius is going to be proportional to 4. Let's make this thing real big. A, T, C, G, C, T, A, G, T, 1, 2, 3, 4, 5, 6, 7, 8, 9. Just for good measure, let's drop another nucleobase on there. So Z is going to be equal to 10, right? Each one of these is going to carry a phosphate on the DNA backbone. Each phosphate is going to have one negative charge, so Z is going to be equal to technically -10, but we'll just absolute value 10. And the size is going to be proportional to those 10 bases that are added in there. The point is that each additional base, nucleobase, that's these things, each additional base adds charge and size at the same rate, right? It gets bigger and it gets more charged at exactly the same rate. That means that the electrophoretic mobility, and I have to apologize, I catch myself doing this all the time. It's mu EP. Sometimes I write my mu's backwards. So if you're getting confused by this, that's always a mu. Mu EP is constant in this scenario. These are three different molecules, but they're all going to have the same ratio of charge and size. And so there's one value of mu EP for these three different molecules. And it turns out that will be true for all DNA chains. All DNA chains, especially double-stranded DNA, which is not what we're talking about here, all DNA chains are going to grow at the same rate in size as they do in charge. We cannot use zonal electrophoresis as a mechanism for separating DNA molecules of different structure. It turns out this is a similar problem in proteins. It's not identical. So proteins act, I'm going to say similarly, but not identical. So proteins, just as a reminder for those of us who maybe haven't thought about biochemistry in a long time, proteins are polymers made up of amino acids. DNA is polymer made up of nucleobases. In DNA, you only have these 4 nucleobases to choose from, A, T, C, and G. In proteins, you have 21 amino acids to choose from. Some of those amino acids have acid-base chemistry, so they'll lead to charge in an aqueous solution. Some of them don't. And so it's not as strict a relationship. As the protein gets bigger, it gets more charged at exactly the same rate, right? It's not as strict. So proteins act similarly, although not as strict of a relationship. But if you think about it, with only 20 amino acids to choose from, as these things get bigger and bigger and bigger, there's going to be some statistical relationship between how big they are and how many charged amino acids have been incorporated into their sequence. And in that case, it means that for very large proteins, there's a very narrow range, not constant, but a very narrow range of mu EP that's possible. So small proteins have a wider range of mu EP. Large proteins have a very, so let's just put the corollary here, large proteins, a very narrow distribution of mu EP. So you can separate them sometimes by zonal electrophoresis, but they become very challenging separations. So what's the solution to this? The one thing we do know about these large proteins and about these DNA molecules as they grow is that their size changes, even if their size to charge ratio does not. And so what we need is a mechanism for separating these molecules by some of these very simple electrophoresis processes, but one that is selective for size, not size to charge ratio. And that is where the concept of gel electrophoresis comes in. So gel electrophoresis, let's draw some kind of electrophoresis. It looks like a capillary, at least in this example. It doesn't have to be a capillary. We'll learn a little bit later. We're going to apply some potential here. And this region that I've drawn here, this is a porous hydrogel, right? So this is porous hydrogel material. So we're going to have some molecules of varying size. You know what? Let's try and show similar size to charge ratio. So let's go 3 times as big and 3 times as much charge. Okay, so 3 very different size molecules, very similar size to charge ratio. Small with 1 charge, medium with 2 charges, large with 3 charges. Okay, we have this porous hydrogel material, and because it's porous, it's got these kind of tortuous paths that can lead through the material. So these lines are meant to imply ways, different paths you can take to get through this thing. Okay, so the hydrogel works as a, I hope I'm going to spell this right, I think it's I before E, sieving matrix. I think it might be E before I in this case, but whatever, you guys can spell check me on this one. Sieving matrix. Okay, so What is a sieve? Um, a sieve is, I mean, you might be familiar with this terminology, you might not. A sieve is, if you've ever seen old-timey um, movies of someone, panning for gold in a river, right? They're using a little porous tray. That porous tray is a sieve. It's something that lets small things fall through, but big things get retained. So that's the general definition of a sieve. This sieving matrix means that it is a lot easier. It is a lot easier for something small to make its way through these tortuous paths than for something a little bigger. Something a little bigger is going to hit constrictions along the way and have to take left turns and right turns, and it's going to come out a little bit later. And something really big is going to have a really hard time getting through. Obviously, these aren't drawn to scale. Something that big with pores that small would never make it through, right? But this is just a conceptual illustration. Something much larger will have an even harder time getting through. They'll come out at different times. We'll get separation based on size alone, not based on their charge. So let's just say here that in the sieving matrix, separation mechanism becomes size based, size only based, not size to charge ratio. Another thing you should know is that very often gels, this doesn't have to be a firm rule, but it is often the case that gels eliminate or dramatically reduce electroosmotic flow. And so that means if these things were anions, actually to make them do this, we would have to reverse the polarity. They'd still go in this direction, but if these all had negative charge, we'd need negative voltage here to push them through. Because there's no EOF, right? So that's the trick. So very often gels eliminate EOF. There are pros and there are cons to doing gel electrophoresis. Let's start with a list of pros. So the selectivity, kind of the whole point, the thing we've just talked about is changing the selectivity of the separation. It becomes size only. There's another thing actually that is kind of beneficial here. One thing we've always talked about fighting, the mechanism we can't get away from in any separation mechanism, but in electrophoresis, is longitudinal diffusion, right? There's diffusion going on here. That's still true. We can't eliminate longitudinal diffusion, but a system like this dramatically reduces longitudinal diffusion, and that's because you remember way earlier in the semester we talked about diffusion in a porous bed. That diffusion coefficient goes way, way down. Your diffusion coefficient is going to go way, way down when you're in a tightly spaced porous bed like this hydrogel material. And so that's going to reduce the amount of longitudinal diffusion you see per unit time. Turns out we're going to pay for that. Let me show you how. So on the con side of things, well, here's the first thing you should know. The A term is back. Remember, our A term refers to the multi-path effect, right? Multiple different routes this thing can take. Porous hydrogel is like a packed bed. There's different ways for these things to go. So our A term is back. The other thing you should know is that heat dissipation, this was kind of a huge focus when we talked about capillaries. Heat dissipation is very poor in these hydrogel environments. And so that limits our E field. Too high of an E field in a system like this, and you'll produce too much heat. So we're looking in gels somewhere in the order of 10 to 50 volts per centimeter. The order of magnitude, at least, maybe 2 orders of magnitude smaller than we're talking about when we talk about capillary zone electrophoresis. Let's see, what else can we say about this? The fact that we have to stick to these low fields means that separation times are long. They can be very long. These things can take hours to do separations on. Long separation time. So here's the other side of that coin. We said we get reduced longitudinal diffusion per unit time here, but we take a lot longer to do it. And so the B term can kill us here. It's not necessary that it will, but the B term can kill us. That longitudinal diffusion can still remain a problem simply because of how much time it takes to do this. Okay. Let's see if there's anything else we should look at. Oh yeah, sure. There's one more. There's one more challenge here. It seems like it's all cons and no pros. One more challenge. A tiny little piece of paper here, so I hope you can read what I'm about to write. These hydrogels aren't typically good optical materials, and that means that a lot of the online detection stuff we talked about in capillary electrophoresis, like shining a laser through this thing, become really hard to do. In fact, usually impossible. These are often done offline um, with dyes, for example, to see your sample after it's separated. So instead of waiting at the end and seeing stuff fall off, usually what you'll do is you'll get a separation in space on this gel, and then you'll image that separation in space. Let's talk about that very briefly here. So gel electrophoresis, we'll call it GE, is typically done not in capillaries, but in what we'll call the slab gel format. Slab gel is exactly what it sounds like. It's a chunk of gel, smaller than, but similar in dimensions or similar in ratio to shape to this piece of paper. So you have a slab of gel maybe that big, and it'll be maybe a centimeter, half a centimeter thick. And so all this electrophoresis is happening inside that big chunk of gel. It's one of the reasons heat dissipation is so poor. You should know that capillary gel electrophoresis, so capillary GE, or we say CGE, is totally a thing. People do this. It's less common. It's tricky to do, and that's because what you're trying to do is fill a very narrow capillary with a very porous hydrogel material, and it's really challenging and far less common. So what we're mostly looking at are these slab gels of DNA. In fact, if you've ever watched like a crime drama and they do like a DNA, like a genetic profile, they show these, you'll see this thing, it looks like it's glowing, and there'll be like all these lines that come down the sheet like this. And they'll look at this and they'll say, aha, it's his genetic profile. What this is a DNA separation. This is a slab gel DNA separation. And this is exactly what they look like. And usually what you do is you do your DNA separation. They separate in space like this. You soak, you don't see them because DNA doesn't have any color, but you soak this gel in a dye that fluoresces in the presence of DNA, and then you shine a black light on it and you see all these glowing lines. So that's a slab gel DNA separation. I'll tell you what, if I can find a nice image online, I'll post that with the lecture today, so you can get a better picture of that. So let's talk about the last thing we'll say on slab gels, and that's that there are two common, I'm going to say formats. Really, it's two common materials used for the slab gel, but the different materials have different applications. So the first one is the agarose gel, right? An agarose slab gel. Agarose is a seaweed derived polysaccharide. Let's see if I can spell that correctly. Polysaccharide, I think. Seaweed-derived polysaccharide. It's a lot like gelatin, actually. It's it's a powder. You mix it with some solution, and it becomes sort of a gel material. You have pore sizes in these. So the trick to selectivity, the trick to making this stuff move, is that the pore sizes inside these gels are the right size to restrict slightly the motion of the kind of the size range that you're looking at. So if you want to look at lots of small fragments, if you want this separation to be, I don't know, 25 base pairs from 100 base pairs, then you want really small pores because those are small DNA fragments. If you want this to be 25,000 base pairs from 250,000 base pairs, then you can have much larger pores because larger molecules are trying to sieve their way through that matrix. So the pore size is an important part of selectivity. Pore size here and also in the other format we'll talk about, depends on the weight percent of agarose in forming that gel. And I'll tell you that it's not a lot of agarose, right? So just like you don't need a lot of gelatin to make a bowl of Jello, your weight percents here are somewhere on the order of, you know, 0.1% to about a really high percentage gel would be like 5% agarose. And the rest of that mass is in solution, is water. So these hydrogels are, you know, at the least, they're 95%, maybe 99.9% water and only 0.1% the sieving material. And so agarose gel is really typically applied to large DNA fragments. Now I'll tell you, I have done these down to about 25 base pairs in agarose, and with a really high percentage, it works okay. But typically, we're talking about thousands of base pairs being separated in your typical agarose gel. Don't see agarose gels used for proteins very much, and that's because protein molecules are a lot smaller, generally more compact than DNA molecules are. And so we need much smaller pores. And so when we talk about protein separation, we're usually talking about the format or the material polyacrylamide. And this is very often abbreviated PAGE, polyacrylamide gel electrophoresis. So if people talk about doing their PAGE separations, this is what they're talking about. What this is polyacrylamide that is cross-linked using usually methylene bis acrylamide as a cross-linker. So you have this two-dimensional gel structure of polyacrylamide. It forms a very clear, actually clearer than agarose, it forms this very clear hydrogel material that is typically applied for small DNA or RNA molecules and far more common for proteins. And that's because you need much smaller pores. That this cross-linking actually produces much smaller pores in these gels. So there's another terminology I want you to know about related to PAGE, and that is SDS PAGE, because it is the most common way of doing PAGE. SDS is our surfactant friend that we talked about in MEKC. So this is sodium dodecyl sulfate, SDS surfactant. It denatures the protein. If you're not familiar with this terminology, denaturing means you have a protein that's folded up like a ball of spaghetti, crunched up. Denaturing is unfolding that ball of spaghetti. So we'll say it unfolds. Unfolds the protein. This is a good thing for getting an apples to apples comparison between multiple proteins, because if you unfold all of them, you're pretty sure that their unfolded size is related to their molecular weight, because there's no secondary structure to worry about influencing their hydrodynamic radius. So the other thing that happens, so the surfactant causes this to unfold, but it's happening because this SDS is very strongly attracted to the protein. So you get this SDS to protein. I'm going to call it binding. It's not covalent. It's just by non-covalent interactions. But you get this SDS to protein binding at a mass ratio, very high mass ratio, of 1.4 grams of SDS per 1 gram of protein. And so basically you can picture these proteins unfolded and completely decorated by non-covalent interactions by these SDS molecules. We saw these SDS molecules. We know that they have charged polar head groups. And so that means that this kind of overall structure, all proteins have a very high negative charge. It's not really from the protein, it's from the SDS, which has its negative charge from that sulfate group. But every protein is decorated with a ton of SDS, and so all proteins look, anyways, like they have a high negative charge. And because everything has a high negative charge, basically it all has a similar size to charge ratio. This allows the separation to be on the basis of size only. Because everything has a similar charge, it's going to have a similar size to charge ratio. All right, folks, that's everything I wanted to say about gel electrophoresis. Friday will be our last lecture in this format before I turn the class over to you guys. So we will talk then about the final and what everything looks like. But until then, I will let you guys get back to quarantine in peace. When we come back, we'll hopefully, I actually haven't planned that lecture yet, but when we come back, I'm hoping we're going to be talking about microfluidics, my particular area of interest, and how it relates to specifically capillary electrophoresis that we've been talking about lately. All right, folks, take care.